So this talk is called From Sparkplug to Drivetrain, Life of an AppEngine Request. And what we're not going to talk about is how to write an AppEngine application. This talk is also, there's no code samples, so no source code. And there's nothing specific to Java or Python. So this is just about the platform and about the architecture. What we do talk about is kind of an overview of the AppEngine platform, how the architecture works, understand the different components in the stack, explore why we built things one way or another way, so design motivations, and what this means for your applications. So the agenda for today is how to design web servers, application servers for scalability. And then we talk about AppEngine and why we built things a certain way. And then I'm going to specifically walk through a life of a request. So when a user request comes in, what happens in AppEngine before that request gets served back to the user? And we'll talk about numbers. So how to design for scalability. Well, Google AppEngine works like this. We have a set of front-end servers. These are like user-facing web servers. All user requests will touch these servers first. But these servers don't contain any special AppEngine capability. They're just generic web servers that work really fast at handling web requests. Behind these servers, we have the actual AppEngine servers. This is where your code runs when you deploy an application to AppEngine. And then we have an app master which controls the configuration of the servers and allocates applications to one server or another server. Now it's very important that we have this separation here, because the AppEngine servers can run your code very quickly and handle response very quickly and then move on to the next request. The connection between the end user and the front-end server may be a slow connection. Maybe they're on wireless in this room, or maybe they're on a mobile network, or maybe they have a very low bandwidth connection. And so it may take a long time to send the response back to the client. So this connection between client and front-end server may stay open for a long time. That means some resources are reserved on the front-end server. So we don't want to waste those resources on the AppEngine servers. And by separating them out, each server can do what it does best. So we take this one step further with specialization, and we serve static files from a different set of resources. So dynamic content comes from the AppEngine server, static files from dedicated. We also have all the backend services are built on specialized systems. We have the data store, the memcache, but also many of the APIs, like the URL fetch, which gets a web page from another site and pulls it in, or the image manipulation that can take an image and put it into a thumbnail or rotate it or flip it. Now, if you look at this architecture, and just kind of remember that in your head. So we have front-end servers, app servers, and lots of specialized systems. Now I want to show you a different slide from 2007. This is from a talk that Brad Fitzpatrick did in 2007, and he talked about LiveJournal, which was a site that needed a lot of scalability. And you see it's a very complex system. There's all these parts to it, and this has grown over a period of time. And many systems look like this. But let me draw some boxes for you to make this a little bit clearer. Really what we have is front-end servers. We have application servers, memcache, data store, static file serving. And you kind of see the same architecture. And so these look very similar. So imagine that you're starting from scratch, and you wanted to set up your own servers in the cloud. You probably start with a LAMP stack. LAMP means Linux, Apache, MySQL, and then probably PHP or Perl or Python. And you have a single server with Apache installed, MySQL, and your software. Everything's running on one server. And you plug it into the network, and all the traffic goes to it, and then your traffic starts growing. And you wonder, is this scalable? Can I handle more traffic? Can I handle 1,000 users or 10,000 users or 1,000,000 users? And you realize pretty quickly that this one web server doesn't scale very well. It's also a single point of failure. If the hard disk crashes, if the machine burns, the power supply is dead, the whole site is down. So as a first step, we might separate the database server and the web server from each other. So we need another machine. So now we have 2 servers, and it's additional management. We have to do the configuration on these 2 servers and keep them in sync and patches on both systems. It's starting to be a little bit more work. The web traffic is still limited to what one machine can handle. So one database server, one web server. And is it reliable? Actually, it's less reliable, because now we have 2 places that can break. This server breaks, site is down. This server breaks, site is also down. So let's go with multiple web servers to handle additional traffic. So we take 3 web servers and 1 database server. That's great. Now we can handle more web traffic, so we can handle more users. Maybe 3 times as much, if we're lucky. But we need more machines, and we have to set up some sort of load balancing so all the users don't go to server 1 or server 2. So first, we try DNS load balancing. We set up 3 IP addresses, and we do kind of a round robin. So different users get different IP addresses. That sort of works, but DNS records have a TTL, a time to live. And not all DNS servers actually respect that value. So when we have a failure of one machine, even if we change the DNS immediately, some users will still be on the old machine, and the site will be down for them until they clear their DNS cache. So we need to do something different. So we install a reverse proxy. That way we control which sites are working. We have the benefit of custom routing. So we can take requests for static URLs, static files, and we can route them to a different server. And that way we can handle more traffic on our main site. And we get application level load balancing, so we can know where the load is the highest and shift traffic around. But we need more machines, and now we need to configure reverse proxies. So now we have to be an expert in SQL administration, we have to be an expert in web server administration, we have to figure out how to configure a reverse proxy. So lots of keyboards and lots of servers. So this doesn't work very well. And we still have single point of failure, obviously. So let's start replicating the database. That way we have 2 databases. If the database goes down, we have another one. That's much better. So all writes have to go to both database servers. So anytime I write anything from any of the web servers, I have to write it to both database servers. The way to do that is you write it to the master, and then use replication to write to the slave as a backup. When you do a read, you can read from this one or this one. Doesn't matter. You'll get the same response. So the benefit is better read throughput. You can read twice as fast or twice as much data because you have 2 database servers to read from. And it's invisible to the application, so your code in the application server doesn't have to change. But we need more machines, and now we have to configure the database for replication. So it's another task that we have to learn and administer. So how scalable is this? Well, it scales with the read rate of the number of servers, but not the write. So we can read more and more and more, but we can't write more and more, because every write has to touch every server. So you may start, if you go from 1 server to 2 servers, you kind of have this transition. 500 writes, or sorry, 500 reads on one server can be split. So now we have 250 reads and 250 reads. But the 200 writes stay the same. It's still 200 writes across all machines. So if we keep pushing more and more users through this, we end up with a picture that looks like this. Maybe we have 400 writes per second, and it's across all machines. 400 writes, 400 writes. Every write has to happen. And we can only get a few reads because capacity is almost gone. So this isn't very scalable. It only goes so far, and then we have to do something else. So is this reliable? Well, we still have kind of a single point of failure for writes. If the master goes down, we're in trouble. And the master can die before replication is done, which is not good. So let's do a partition database instead. Let's take our one big database and we chop it into lots of little pieces. So some of the customers live here, other customers live here, other customer data lives here, more customers, more customers. And so we have lots and lots of databases. And my data lives here, and your data lives right here. And this is probably, it helps with scalability because we can increase both the read and write throughput. Because now those 400 reads, they can be split across, say, 4 machines, and we have 100, 100, 100. So we can increase our scalability. But we need even more servers. There's lots of management overhead. Now we have MySQL configured with replication and sharding, and we have to replicate maybe some lookup tables, and it's just a very complicated environment. We have to change our data models, because we can't select star from 5 databases. We have to select star from this database, from that one, and then merge all the results together. So that's quite difficult. Now we've built all of this up. Why not just use Google AppEngine? It does all this for you. It scales the data store for you. With AppEngine, the more data that you put in the data store, the more distributed it becomes. And when you start with AppEngine, on day 1, it's distributed. So this slide with lots of little databases, and lots of web servers, and load balancing on the front end, all of that is included in the AppEngine platform. So as you saw earlier today, all you do is you take your code, you upload it, and then it's hosted on AppEngine. So let's look at some of our design motivations. What we wanted to do when we built AppEngine, we obviously wanted to make it easy for you to build applications, easy for you to maintain them, easy to make it scalable, but we were also thinking about ourselves. And we wanted to build on existing Google technology. We have lots of services and software and infrastructure at Google that we don't have to build because it's already there. We wanted to provide an integrated environment. So you just have one place, one administrative console, one SDK where you can do things. We wanted to encourage you to make small requests. And there's lots of reasons for that. It helps with load balancing. It helps with the better design of your application. It helps with the distributed platform. It also helps make requests fast and efficient. And it helps us maintain isolation between applications. If your application has one very large, heavy request, and we put it on this server, then other applications on that server might be affected. But if we have lots of little tiny requests, we can spread them out and move them around, and you get better utilization. And we wanted to encourage statelessness and separation. Statelessness means that I can make one request to this server, and the next request can go to this server, and I can get the right answer. I don't need a sticky session, no sticky IPs. Sessions can be global, applications can be moved around. If I have 10 servers and I need to reboot one, I can just hit the reboot button. And the next user comes in will hit a different server and still get handled. So let's look at the life of an AppEngine request, what happens from start to finish. So when you in your web browser, you go to appspot.com and you go to your domain for an AppEngine site, you get routed to the nearest Google data center. And then over the Google's network, your request gets transmitted to the data center that hosts the AppEngine server. And we get a lot of benefits from this. We get to travel over a faster network. We get to optimize the network configuration parameters on this backbone. And the edge of the network, when the request comes in and hits a local data center, is very close to the user. There's a short ping time, so that if there's communication that needs to happen, maybe for dropped packets or retrying functionality, there's a very short latency there. Even though the total distance to AppEngine might be long, the effective communication distance is to the edge of the network. So first I'm going to do the simple thing. Let's look what happens for static content. So maybe I have a CSS file or index.html, which is static. So the request comes in to the front ends, and they take care of load balancing and routing. And they route the specialized request to the static content servers. So the AppEngine servers aren't even used. These are separate servers altogether. Now these special content servers are built on existing Google infrastructure, and we have many properties, many web services that need static files, and we just use the same service across all of these. So to implement this in AppEngine, we simply took that Google service and put a thin AppEngine layer front end on it and are able to serve it, which is one of the reasons that we can deliver features very quickly. Now you might wonder, so how do you set that up in your application? Well, for Java, you simply in your AppEngine web XML, you can specify the static files. If you're using Python, you can do that in your app.yaml. Now, once the request has been made, the static content needs to be served back to the user. The response for the static content, maybe it's a large file. Maybe it's a 1 megabyte file. It gets sent to the front end very, very quickly. This is happening over the Google network. These are fast servers. And as soon as that 1 megabyte file has been sent to the front end server, the static server is done. It can serve the next request and the next request, so it can handle the scalability. The front end server will talk to the web browser and send the bytes down. And if it's a slow connection, it will send the bytes slowly. So only the web server is tied in the request. The rest of the back end is freed up from resources. Now let's look at a slightly more involved example with dynamic content. So the front ends, they route all the traffic to the AppEngine servers, and that's where your software runs. The app master kind of schedules applications. So if your application requires more servers because you have more traffic, the app master will assign more web servers. If you get less traffic, the app master will remove servers from your application. So a request comes in from a user for some dynamic content. It checks to see if there's already a cached runtime. That means a cached version of your application. If it exists, then it can just handle the response immediately. If it doesn't, it spins up a new runtime environment. It executes the request, and then it caches the runtime environment for next time. So it's a little bit slower in the first request. If your application has been idle for several minutes and you have no traffic, you might see that that first request is kind of slow and costs a little bit more CPU time. But it's much faster in subsequent requests. So the second request can be really fast. If you have a lot of traffic, then you'll have a lot of app servers that are always available and running. And you should see that the vast majority of requests are handled quickly. So what do the app servers? Well, they do. They run many applications. So there's many applications on one app server, or you might have one application that runs on many app servers, depending on the traffic. They run many concurrent requests. So they can be used very efficiently. They're always, we try to maximize the use on every app server. They enforce isolation, so your app can't talk to someone else's app, and your data can't be accessed from someone else's app. They enforce statelessness of your application, and they provide access to all the back-end APIs. So if you want to get to the data store or memcache, you can do that via the app server APIs. So let's look at that example, accessing the APIs. So we have the app servers, and what they do is they issue an API call. So maybe they talk to the images API and say, please create a thumbnail of this image. So this big image, turn it into a smaller one. And the app server then pauses and waits for the response. So you should use these APIs to do things that can be done more efficiently by specialized services. And here's just an example of some of those specialized services. You recognize some of these, like email is just mail delivery. XMPP is for chatting, like you can robot with a talk. The user API is a special case where you can allow Google to control the authentication of your application and make sure that there's someone always logged in, or you can control it for you. Now I want to talk about memcache, because if you're going to do any type of large application with scalability, you want to use memcache. You should know this, and I'm sure you do, that accessing memory is much faster than accessing disk. There's just, the physical world means that memory is faster. With the disk is spinning around and the head has to move and then wait for the right sector to come underneath, and then it has to start reading. That can take, just the seek itself can be 10 milliseconds. Whereas in that amount of time, you can probably access a block of memory and transfer it. Now with memcache, we've done something very special. Instead of just a local cache on the machine, we've taken lots and lots of machines and grouped them all together. And those machines function as a single whole, a set of memcache servers. And what you can do is make an API call to this large bank of machines, and you say, set this value, or retrieve this value. And you kind of get like a big hash map. You can put key values in and get key value pairs out. Now when you think about this, think about very large systems. I believe Facebook has the largest memcache instance around, at least that's publicly talked about, and they have terabytes of memory. So think about how many machines you need to have all together that have terabytes of memory, and all those machines are doing is storing key value pairs for your environment. And think of how fast you could get information. The API that you're probably going to be dealing with the most is the data store API. This is how you persist data. This is how you write data to disk and keep it there. It's based on Bigtable. Bigtable, there's a white paper you can read. It's a very scalable, distributed data store system. It's row-based. You get transactions at the row level. And for AppEngine, we've created another layer of abstraction above Bigtable, which allows you to have entities and entity groups. Now, there's a number of benefits to the data store. The first is that your data is partitioned from day one. So if you remember that earlier slide where you have lots and lots of MySQL servers, and it's a lot of work to set those up, and a lot of work to, if you want to double the number. With AppEngine, you just put more data in the system. And the more data you put in, the more distributed it becomes. And it just happens automatically for you. We have a system of explicit indexes. Some are created automatically for you, but we have indexes so that most queries can be answered by a quick index scan and then fetching relevant entities. We take care of fault tolerance. When you commit to disk and the commit returns successfully, your data is stored on at least 3 disks, 3 physical disks. And then usually a few moments later, that data is replicated to another data center. But what you can know is that once you commit, the data is written to 3 disks. Now, these APIs are all based on existing services. And so you recognize the mail API. Obviously, we do a lot with mail. Gmail needs a lot of incoming and outbound email capability. And all that service and infrastructure that's used for Gmail is the same service and infrastructure we can use for AppEngine. With URL fetch, we crawl the web. We search the entire web and find websites and rank them and index them. That same infrastructure that knows how to fetch URLs is what we use in AppEngine to allow you to integrate with other applications. So you can call webhooks. The image manipulation, the thumbnailing and flip and rotate API, is the same one that we use on Picasa Web. And the XMPP API is the same one we use for Google Talk. So you can see how we can quickly roll out new services. So this is a secret picture of a Google data center. And you can see the AppEngine servers there in the very back. And the guy with the glasses, he's the app master. So let's go over the kind of the design motivations again and see how that works out. We said we wanted to provide an integrated environment because we want to be able to manage all the applications together. And what does that mean for you when you write an application? Well, it means that you're encouraged to follow best practices, but it also means there's some restrictions. You don't have access to a local file system to read and write files. You can't open arbitrary network sockets. Requests are limited to 30 seconds each. There's no relational model between entities. So you have to work a little bit differently than you do in an SQL environment. It means that you need to use the tools, the AppEngine tools for the platform, but you also get some benefits. For example, you get to use the AppEngine tools for our platform. You get an integrated admin console where you can easily find logs, you can configure your application. All the logs are in one place. I don't know about you, but every time I work in my past life on an application stack, it's always very hard to find log files. Usually you have, say you have 4 web servers, and you have 4 access logs, and they're on different machines. And then your application server has 4 logs. And all the requests from all users generate log messages that are all intertwined with each other. And you have errors and success and access logs. And then one of your users reports a problem. They said, this morning I had a problem. So you say, well, what time? 10. Oh, what time exactly? Well, I don't know. Okay, when it happens again, tell me. So they tell you. 12:31, I had a problem. Okay, so you look through all the logs, 12:31, see, I found an error message. Big stack trace. Okay, so what was the request? I don't know. Let me find this other log file. Maybe I can use the session ID to correlate this log file with that log file. We've all done this, right? It takes forever just to find the right messages. Well, with AppEngine, all the logs are together. So for every request has all the log messages in your application, any error logs, any AppEngine logs, they're all integrated in one place. So you go to the admin console, you can just filter by error, you can open those requests, and you can see the entire context. That has made a really big difference for me in trying to debug an application and figure out what's going on. And we have no machines to manage or count. This is a small bullet here, but this is a pretty big deal. Remember the slide where we had all these database servers and web servers, and we had to have root access everywhere, and we have to log in and configure this and apply patches. And we have to know how many servers to build. Do you know how much traffic you're going to get next week? When you build an application, do you know how successful it's going to be? What if it's shown in the news? What if it's very popular and suddenly lots of users come? How do you provision enough servers? What do you do? How do you make sure you don't provision too many servers that cost too much money? With AppEngine, we automatically adjust the number of servers for the current load of traffic volume. So if right now you have lots of requests, we assign lots of servers. If an hour from now your application is idle, then we use those servers for something else. And you saw how easy the deployment was earlier today. Push deploy, your software is uploaded, that's it. It's hosting. We wanted to encourage small per request footprints, so we get better utilization of app servers, we get fairness. It does mean some restrictions for your application, like less memory that you can use in the application. Instead, you have to use the data store and memcache. We wanted to encourage fast, efficient requests, and that means you should probably use caching. Anyone who's done any amount of work in AppEngine knows that memcache is the secret. When you start using memcache, your application gets faster. We can get better throughput that way. We can get better fault tolerance and really better use of resources. I'm just going to skip over this one. Here's the important one, require partition data model. So this is the thing that most people talk about when they start with AppEngine. They come from an environment where they're used to SQL, right? You use MySQL and Postgres or some commercial database, and you're just very familiar with it. You know how to write SQL queries, you know how to do updates, inserts, deletes, and then you come to AppEngine, and there's no joins. You can't join this with that. We don't. And so in the beginning, it's a little bit difficult to deal with. But every time I ask someone who's worked with AppEngine for a few months, I ask them, is it easier on AppEngine or is it harder on AppEngine? AppEngine or SQL, which one? And the answer is pretty much always, they're the same. They're both easy, they're both hard. Not one is easier or harder than the other. They're just different. And they're a different set of tools for a different type of problem. And the benefits you get from AppEngine is because there's no joins between these tables, we can make your data model very distributed across many different machines. And so we get really good scalability. And you can imagine the scalability if I have a request coming in for this user to this web server, which connects to this database server. And I have a different request for a different user connecting to a different web server, and it only has to touch a different database server here. These two servers share nothing with each other. So that scales very well. This request can't slow down this request because they touch very different machines. And I can just replicate that. That's horizontal scalability, where I can just keep going and add more servers and insert more data and get more scalability. The vertical scalability really doesn't work very well. You can try to buy a bigger server, and you can try to buy faster disks and faster CPUs and more CPUs, but it's very limiting. At some point, the machine won't grow. Horizontal scalability is really the only way you're going to get meaningful scalability. So let's just talk about AppEngine numbers where we stand today. We have about 100,000 applications deployed on AppEngine today. It's probably a little bit more. Each day, the entire platform serves about 250 million page views. That's across all applications. And there are about 250,000 developers that maintain these applications. And we have currently 2 supported languages, Python and Java. But because we run the Java JVM, there's a number of other languages you can play with, JRuby, Groovy, Scala. There's even support for PHP on top of Java. The Quirkus has a solution for that. And if you want to find out about different frameworks, you can go to this URL right here. Look for Will It Play in AppEngine, and you'll find a site that talks about all the frameworks and the languages. Now I want to just close with this slide. This is a little traffic graph of Google Moderator, which was used for an event by the United States White House. They had a kind of a town hall where they asked citizens to vote questions, and after 2 days, the president would answer the most popular questions. And you see, this is the traffic graph of the users coming into to the site. And what you see is right before the deadline, you had the high peak of about 700 queries per second. So this is the maximum traffic that AppEngine had to deal with. Now, if you had to build this on traditional servers, you would have to guess how much traffic was going to show up and then provision. If you over-provision, then you have idle capacity that you paid for that you don't need, so that's wasteful. If you under-provision, then your site can't handle the traffic. Now let's say you're really good with numbers, you're really lucky, and you get exactly 700. You buy enough servers for 700 queries per second, perfect. But look at that, you only needed it for a few minutes. The rest of the 2 days, you had lots and lots of idle time that would be wasted. With AppEngine, we spin up more servers when there's more traffic, and we spin down when there's less. And we do it completely automatic. So there's no knobs to turn, dials. I want to leave you with the AppEngine URL. This is where you can find documentation, online forums. You can download the SDK. If you do want to download AppEngine and you work with Java, I'd recommend you use the Google plugin for Eclipse. And the plugin for Eclipse will download the Java and the Google Web Toolkit SDK for you. So if you want to use Python, you go here and just download AppEngine directly. If you want to use Java, download Eclipse, the Google plugin for Eclipse, and then it will download the rest for you. Thank you very much. Do we have any questions right now? Yes. So the question is, how much did the White House event cost? And I'm not sure. I don't have the precise numbers, but so this application, just like any other, will get the first roughly 5 million page views if it's well written and it's a typical application free for that month, and then they pay for the resources above that. So CPU used, data store used, disk used. I'm sorry I don't have a number for you. Any other questions? Yes. Okay. So the question is, if I host my site on AppEngine and I get a denial of service attack, so someone else tries to bring my site down with sending me lots of traffic, well, how does Google protect me? And well, so the answer is that it depends on the scale of the attack. So if you just get lots more traffic, then we will actually just serve lots more traffic. If it looks like legitimate traffic. There are things you can do in your application. If you recognize that it's not valid traffic, you could deny the request yourself. For example, if your application is protected with Google login, then the users have to log in before they can do anything. If that traffic exceeds the quota that you've paid for, then you would run out of quota for that day. So the question is, are there any thresholds or notifications when you go beyond the quota? And the answer is that's on our roadmap to do in the next few months. That is frequently asked. People want to be notified when they're close to the quotas, or if there's any issues with their application, or if they need to update something. So we're definitely working on that, and we haven't decided, I think, precisely how we're going to do it, but I know people have asked for email notification, SMS notification, and they've asked for all sorts of configurations. So in the next few months, I expect we'll have something. For now, you can do two things. You can log into the admin console and look and see, but there's also third-party monitoring that you can do. So you can just have another website do an HTTP request to your application, and if it serves successfully, then you know your site is working. So what are the restrictions for applications in AppEngine, like read access to files, that sort of thing? Okay, so the AppEngine sandbox is, the restrictions that are there are kind of two types. They're there for security reasons, and they're there for scalability reasons. So AppEngine is a distributed platform, and if one request can come to this server and the next request to that server, it doesn't make sense to access the local file system because each request can be on a different machine. Also, from a security perspective, you don't want generic access to the file system. So what we do is give you the distributed data store instead so you can put transactions in. You can't open network sockets, so you can only make HTTP calls. But if you need to access other protocols, like you need to access a database, we do have a secure data connector that you deploy on site behind your firewall that connects to AppEngine. And then your users contact AppEngine. AppEngine connects to the secure data connector behind your firewall. And then you can have an adapter there that talks to a database server or a web service or something else. There are other restrictions like all requests currently have to finish within 30 seconds. So even background tasks with task queue have to complete quickly. And what we'd rather see is many, many little tasks. So if, for example, you have 1 million customers in the data store, and you want to touch every single row for every customer and do some sort of update. In the SQL world, what you would probably do is you write a big update statement. Update customer, set, where, like that. And then you hit enter and you just wait. And then maybe it runs for 20 minutes and then it's done. Or you might write a program that iterates through all the values. On AppEngine, what we'd have you do is iterate through all the entities and create a task for every entity. So you end up with 1 million tasks. And you throw them in a task queue, and AppEngine will spin up additional processes just like its number of requests coming in. And you set the rate, so you control how fast it will go and how many tasks per second or per minute can be handled. And then we'll chunk through that data very quickly. Also on the roadmap is a feature to make this a little bit easier. Today, you have to kind of loop through all your entities to create the tasks. What we want to do is allow you to say, for this type, for this entity type, assign this task to all entities. And then we do the work of creating the million entities, or million tasks for you. Okay. Thank you, everyone. See you at the next session in office hours.